I'm Dario, and in this presentation I will overview the architectures and functions of River, an eBPF-based runtime verification platform for cyber-physical systems. Let's start from a brief introduction. River is currently implemented with a client-server architecture. The server allows a client to perform monitoring, classification, and runtime verification tasks on a CPS model provided as a binary program. In detail, the client selects the tasks to be performed and tells the server the desired input signals and internal state variables to be supervised. The server then starts supervising the CPS leveraging the eBPF technology. Dedicated eBPF programs preempt the CPS during the execution of the loop cycles with two goals. The first is to log the CPS trajectory, and this is performed by periodically polling the collected information and by saving it to a key value store. And the second is to alter the CPS behavior at runtime with the injections of values to signals and internal variables, which are sent by the client via network. Let's now move to the demo. I will demonstrate some of the functions provided by River using two well-established models: an abstract fuel control system and an adaptive cruise control system. Let's consider the fuel control system first. As you can see, it was developed with Simulink and it contains several subsystems. It receives as input the pedal angle and the engine revolutions per minute, and outputs the air-fuel ratio together with the controller mode. After the system design is performed, the model is automatically translated into a source code using the MATLAB embedded code generator. In this case, it was converted to a C project and compiled as a standalone binary. Let me show you the execution. Okay, we want to simulate the execution of this model with River. So let's first rebuild River from scratch, and let me also start a dashboard that will be useful in our simulations. So let's run the previous model and then explain what happens. I have a list of demos here, and we want to execute a signal perturbation simulation. The model in my environment is model 3, and the configuration I would like to show you is configuration 2. Okay, let's execute and then let me explain what happened. So the client sent to the server a network request with details about the initial trajectory, the input-output signals to watch, and the duration of the simulation in terms of number of cycles. The server then initialized the model and started its execution. For every execution cycle, the server supervised the model, performing the required writes and read operations, and then the output was collected automatically by River, organized into batches, and then transferred to the key value store, where it was logged where it is read by the dashboard and visualized. As you can see, we have complete visibility of the trajectory, and we have a time series for each of the signals requested by the user. Now let's have a closer look at the configuration file and at the trajectory. So this is the configuration file for the task we have just executed. As you can see, there is the path of the model that needs to be executed. There are other details about the simulation, for example, explaining to the server when the CPS can be stopped. And most importantly, there are three blocks of signals: input signals to write, input signals to read, and output signals to read, together with their memory addresses. Let me also show the trajectories. So it was model 3, configuration 2. All the client has to do is prepare a Python dictionary and associate a list of values to each signal. For example, here you see the angle and the revolutions per minute. And of course the same can be done with the perturbations, with the difference that the perturbations are applied at runtime while the simulation is running. Now, I would like to show you a second example based on the adaptive cruise control system. In this case, we have a lead car that is part of the environment and an ego car which tries to follow the lead car but needs to keep a safety distance, a certain safety distance. And in this case, it's this model, and we are going to operate on this D relative internal signal. So on my system, this is model 1, and again I'm going to perform a signal perturbation simulation. So model 1, and what I want to show you is the configuration 2. So let me run again the simulation, and as you can see, the cache has been cleared, and now we have a variation of the relative signal that of course varies with the velocity of the ego car. Now let me demonstrate at last a key function of River, which is the modification of the model internal state at runtime. And to do that, I am using this very simple model which just perform the addition x plus y, one addition per second. What you don't see from this interface is the presence of an internal offset that can change the result. It is by default set to 0, and it will be changed during the simulation. So let me go back, and now let's just filter the live events, the live injections that occur during the simulation. So this is a state perturbation simulation. The model is model 2 on my environment, and the configuration is configuration 1. So I start the simulation, and as you can see, the simulation starts. And only after the simulation was started, the client sent a perturbation of the state via a network, which appears here on the debug log. So it arrived at time 2 while the model was executing the third step, and in this case it affected time 5. So what happened is that this request was registered, and when the model arrived at evaluating step 5, the perturbation was actually injected by the server into the model. You can see this from the live dashboard. So at time equal to 5, this internal offset was set to value 50, and from time 5 until the end of the simulation, it permanently affected the result of x plus y. So now let's move to the conclusions. We have presented River, an eBPF-based platform supporting monitoring, falsification, diagnostic, and runtime interventions. So it helps developing attacks, and it helps designing and evaluating enforcement techniques. Compared to existing solutions, there is no need to access the source code, there is no need to compile the application, and it can operate online because it can handle perturbations while the model is executing. And it also gives access to both the input-output signals and to the internal state. The code is publicly available at this link, this repository, and thank you for your attention.